Hey everyone, if you've ever wondered how the invisible forces between tiny atomic particles actually scale up to store the energy that powers your smartphone, well, you're in the exact right place. Let's dive into this explainer and unpack Chapter 2, breaking down the fascinating mechanics of electrostatic potential and capacitance. We're going to turn some pretty rigorous textbook theory into a clear, easy-to-follow roadmap. I mean, think about it. You can't just scoop up electrostatic potential in a jar, right? And you definitely can't weigh it on a scale. So how do we capture it? How do we actually quantify a force that exists essentially as an invisible property of space itself? Well, by the end of this chapter explainer, you're going to see exactly how we trap this ghost in the machine. Here is our roadmap for the chapter. First, the gravity of electricity. Second, mapping electrostatic potential. Third, the energy of charged systems. Fourth, the electrostatics of conductors. And finally, capacitors and energy storage. Let's jump into part 1, the gravity of electricity. So picture lifting a really heavy box off the floor. You're doing work against the conservative force of gravity, and that work actually gets stored as potential energy. If you let it go, boom, it falls, and that potential energy converts straight back into kinetic energy. The Coulomb force between two stationary charges behaves exactly the same way. Both of them have this inverse square dependence on distance. Honestly, the only real difference here, we just swap out the word mass for charge, and suddenly we're dealing with electrostatic potential energy. You know that feeling of trying to push two identical magnet poles together? How they just want to instantly snap apart? You have to physically push them together, applying your own external force. It's the exact same vibe here. We're moving a tiny test charge Q toward a larger charge Q against a repulsive force. We bring it in infinitesimally slowly, no accelerating. And the work you do pushing it from point R to point P, that is stored purely as potential energy. And here's the best part. Because this is a conservative force, it doesn't matter if you take a perfectly straight line or some crazy zigzag path to get there. The work done is exactly the same. Moving right along to section 2, mapping electrostatic potential. Okay, here is a massive takeaway for this chapter. The absolute value of potential energy doesn't really matter. Physically, it's only the difference in potential that actually means anything. Think of it like measuring altitude. Saying a mountain is 5,000 feet tall implies it's 5,000 feet above sea level, right? Sea level is our zero reference point. In electrostatics, our sea level is just infinity. So the electrostatic potential at any given point is simply the work required to bring a unit positive charge all the way from infinity to that exact spot. But in practical, real-world circuits, we really only care about the potential difference between two specific points. Now flip that idea and imagine walking along a perfectly flat mountain ridge. You aren't hiking up and you aren't hiking down. You're at a constant altitude, so you aren't fighting gravity at all. An equipotential surface is the electrical equivalent of that flat ridge. For a single point charge, these surfaces form concentric spheres radiating outward. And because the potential is constant across that entire surface, zero work is done moving a test charge along it. Absolutely none. Because of that, the electric field is always acting at a perfect right angle to these surfaces. It's acting like a guide, pointing straight down the steepest potential hill. Think about it. If the electric field wasn't perfectly perpendicular, it would have a component pushing along the surface itself. And if it pushed along the surface, moving a charge would require work, which directly breaks the whole definition of an equipotential surface. So electric field lines and equipotential surfaces are forever locked in this perfectly perpendicular dance. Which brings us to section 3, energy of charged systems. Let's build a system from scratch. Picture a completely empty universe. You bring in your very first charge, Q1. It costs you absolutely nothing, zero work, because there's no existing field to fight against. But now Q1 is sitting there projecting its own electric field. So when you try to drag charge Q2 in from infinity, you have to actively push against Q1's field. That takes work. If you want to bring in a third charge, Q3, well, now you have to fight against Q1 and Q2. The total potential energy of this entire system is simply the sum of all that external work you did to assemble it piece by piece. Okay, let's ground this a bit in section 4, electrostatics of conductors. So what happens when we apply these abstract rules to solid materials, like a chunk of metal? It creates an incredibly elegant self-balancing act. Because electrons in a conductor can move around freely, they instantly rearrange themselves to totally cancel out any internal electric field. That's why E equals 0 inside. Any excess charge just gets shoved directly to the outer surface. And since the internal field is zero, the entire volume of that conductor, inside and out, sits at one single constant potential. Finally, the payoff. Section 5. Capacitors and energy storage. This is where all that abstract theory becomes real, tangible technology. A capacitor is so beautifully simple. You just take two conducting plates and separate them with a tiny gap of air or an insulating material called a dielectric. By piling a bunch of positive charge on one plate and negative charge on the other, you create this incredibly confined electric field right between them. Its capacitance, meaning its raw ability to store this charge, depends entirely on the physical shape of the plates and the insulator stuffed between them. Now, when you're building circuits, the way you physically wire these capacitors together completely flips the math. If you wire them in parallel, it's like you're building one giant megaplane, so you literally just add their capacitance values together. Super easy. But when you wire them in series, the total capacitance actually drops, and you have to calculate it using their reciprocals. This is absolutely crucial to understand if you're trying to design a circuit with a very specific energy storage capacity.
And here is the magic formula for finding exactly how much electrical energy we've managed to trap inside that capacitor. U equals 1/2 times the capacitance times the voltage squared. Notice that squared voltage term. That is a huge deal. It tells us that if you just double the potential difference across your capacitor, you don't just double the stored energy, you literally quadruple it. And hey, look at the math. It is exactly the same format as the kinetic energy of a moving object, 1/2 mass times velocity squared.
So what should you take away from all this? Mastering these fundamental, slightly abstract concepts literally gives you the blueprint for controlling electricity itself. We started this explainer by imagining test charges floating in an infinite empty void. And we use those exact same rules to build the mathematical foundation for capacitors, the vital, everyday components sitting inside your laptop, your car, and the entire global power grid right now. I'll leave you with this one final thought from the chapter to chew on. We just learned that a hollow cavity inside a metal conductor is completely immune to outside electrical influence, perfectly shielded, even from a lightning strike. So, as we build more and more hypersensitive electronics and try to protect our own biological systems from everyday electromagnetic noise, how might we better use this bizarre, perfectly balanced quirk of physics to isolate our environments? Thanks for joining me on this explainer, and remember to keep questioning the invisible forces all around you.